This video is brought to you by mywayteaching.com.
So in this part, let us study about one of the important application of Kirchhoff's law, that is Wheatstone bridge. Okay, you can consider the circuit in this figure. This is called as Wheatstone bridge, and this bridge, it has four resistors R1, R2, R3 and R4. Across one pair of diagonally opposite points, a source is connected, isn't it? A and C. In this figure you can A and C. And this is called battery arm. Okay. Between the other two verticals, that is B and D, this one, between A and C, a source is connected, that is called as battery arm, and between B and D, you can see there is a galvanometer arm. We call it as galvanometer arm only. Okay, this galvanometer is G, it is connected between B and D. So for simplicity, let us assume that the cell has no internal resistance. Okay, the cell has no internal resistance, which means we'll consider for simplicity R is equal to 0. So in general, there will be currents flowing across all the resistors as well as current Ig through this galvanometer G, isn't it? So of special interest in the case of a balanced bridge where the resistors are such that Ig is equal to 0. Only if it is a balanced bridge, then we can consider Ig as 0. Then we can easily get the balance condition such that there is no current through G. If there is no current through G, then we can say it is balanced bridge. So the Kirchhoff's junction rule applied to junctions D and D. In this particular figure, the junction rule is applied to D as well as B. Okay. So immediately it gives us the relation, that is I1 is equal to I3. If you apply junction rule at B and D, it gives this relation only. Current entering the node is equal to current leaving the node. So now we apply the Kirchhoff's second rule. Okay, that is Kirchhoff's closed loop rule to the loops AD, BA. And CB, DC. Then this first ADBA loops, it gives us the values, that is minus I1 R1 plus 0 plus I2 R2 is equal to 0, because current through galvanometer is 0, so this 0 is for that. Now the second loop gives, using this conditions, that is I3 is equal to I1 and I4 is equal to I2. If you use this, then this second one gives I2 R4 plus 0 minus I1 R3 is equal to 0. So then from this first equation, we'll get I1 R1 is equal to I2 R2, isn't it? So then we can write I1 by I2 is equal to R2 by R1. Then from the second equation, we got this, that is I1 by I2 is equal to R4 by R3. So we can write R2 by R1 is equal to R4 by R3. So this last equation relating the four resistors, We call it as balance condition for the galvanometer to give zero or null deflection. Okay. And the Wheatstone bridge and its balance condition, it provide a practical method for the determination of unknown resistance. Let us suppose you assume we have an unknown resistance which we insert in the fourth arm. R4 is thus not known. Okay, if you consider, so if you insert that unknown resistance R4 in this fourth arm, then using this equation, that is R2 by R1 is equal to R4 by R3, we can find out that unknown resistance, isn't it? And from this balance condition, the value of the unknown resistance is given by R4 is equal to R3 into R2 by R1. Okay. A practical device using this principle, we call it as a meter bridge. Meter bridge works on this principle only. Now let us see one simple example. The four arms of a Wheatstone bridge, as you can see in the coming figure, have the following resistances. AB is equal to 100 ohm, BC is equal to 10 ohm, CD is equal to 5 ohm, DA is equal to 60 ohm. So here, a galvanometer of 15 ohm resistance is connected across BD. Calculate the current through the galvanometer when a potential difference of 10 volt is maintained across AC. So, this is the question. First, let us consider the mesh BADB. Okay, BADB. We'll consider that mesh first. So, if you consider that, then we can write the equation 100 I1 plus 15 IG minus 60 I2 is equal to 0. Isn't it? Or we can also write 20 I1 plus 3 IG if you take 5 common minus 12 I2. Okay. Considering the mesh BCDB. Now, if you consider the mesh BCDB, we can get the equation, that is 10 I1 minus IG, isn't it? So here 10 I1 BCDB minus 15, we are moving like this, BCDB minus 15 IG minus 5 I2 plus IG is equal to 0. So if you simplify this, we get 10 I1 minus 30 IG minus 5 I2, that is equal to 0. So 2 I1 minus 6Ig minus I2 is equal to 0. So these are the equations for two mesh. If you consider the mesh that is ADCEA, okay, ADCEA, this mesh, then we get 6I2 plus 5I2 plus IG is equal to 10. That is 65I2 plus 5IG is equal to 10. So if you simplify it further, and multiplying the equation that we got before by 10, the equation 2I1 minus 6IG minus I2 is equal to 0. If you multiply this equation with 10, we get 20I1 minus 60IG minus 10I2 is equal to 0. Okay. Then from this equation and the equation that we derived earlier, that is 20I1 minus 6IG minus I2 is equal to 0. So if you simplify these two equations, we'll get the simplified equation, that is 63 IG minus 2I2 is equal to 0. So I2 is equal to 31.5 IG. Okay. Now substituting the value of I2 in the equation, that is 13I2 plus IG is equal to 2. In this, if you substitute the value, we'll get the value of IG, that is given by 4.87 milliamps. Okay. Now let us study about the meter bridge. Okay. See, this meter bridge, it consists of a wire of length 1 meter. As you can see here, it consists of a wire of length 1 meter and of uniform cross-sectional area stretched taut and clamped between two thick metallic strips bent at right angles. So these are the metallic strips which are bent at right angles, and it has a length of 1 meter, and the metallic strip has two gaps. You can see here, these two are the gaps across which resistors can be connected. So here we have connected the resistor R and even the resistor S. The end points where the wire is clamped are connected to a cell through a key. So it is connected to a cell through this key. One end of a galvanometer is connected to the metallic strip midway between the two gaps, isn't it? So here you can see this galvanometer, and the other end of the galvanometer is connected to a jaw key. Okay, it is connected to a jaw key here. The jaw key is essentially a metallic rod whose one end has a knife edge which can slide over the wire to make an electrical connection. So this jockey, it will slide on this wire to make this electrical connection possible. And R is the unknown resistance whose value we want to determine. Okay, and it is connected across one of the gaps. Across the other gap, we connect a known resistance, that is S, that is standard resistance. Okay, and the jockey is connected to some point D on the wire. This one, this is a point D. Here jockey is connected. On that wire, a distance L centimeter from the end A. From this end A, this is at a distance of L centimeter. And this jockey can be moved along this wire, the portion A, D of the wire has a resistance RCM L, where RCM is the resistance of the wire per unit centimeter. And the portion DC of the wire, it has a resistance that is RCM 100 minus L. That is RCM L. This is RCM 100 minus L. And the four arms AB, BC, DA and CD. Okay. AB, BC, DA and CD with resistance RS and RCM L and RCM 100 minus L. Obviously, it forms a weak bridge with AC as the battery arm, isn't it? And BD as the galvanometer. You can see here this BD, it is a galvanometer, and this AC, it is an arm of battery. So if the jockey is moved along the wire and BD is the galvanometer arm. Okay, if we move this jockey along the wire, then there will be one position where the galvanometer will show no current. So let the distance of the jockey from end A at the balance point is equal to L, which is equal to L1, where current is 0. Okay. And the four resistance of the bridge at the balance point, if you consider, one is R, one is S, one is RCM L1 and the another one is RCM 100 minus L1. So if for the balance condition to occur, we know what is that condition, that is given by R by S is equal to RCM L1 divided by RCM 100 minus L1, okay, which is equal to L1 100 minus L1. Okay, once we have found out L1, the unknown resistance R is known in terms of the standard known resistance S. So we can write R is equal to S L1 by 100 minus L1. By choosing the various values of S, we would get various values of L1 and calculate R each time. And even an error in this measurement of L1 would naturally result in an error in R. That we can show it using percentage error, and it can be minimized by adjusting the balance point near the middle of the bridge when L1 is close to 50 centimeter. Okay.